So yesterday we left off by noting that if you increase the number of subintervals, you get a better looking rectangle. That is, there's less wasted space. It's not quite as boxy. And then we said, let's see during our next lesson how the calculator can aid us in maybe getting some of these ramps. Well, I'm talking specifically about the calculator programs. So what you're going to want to do is you're going to want to take out your graphing calculator. Very likely I'm going to show you some new menus and some new buttons. Of course, mainly in showing you how to operate the programs that got downloaded the other day. So get out your graphing calculator and turn that thing on. Find the program button. It's right here in the middle, PRGM. If the program's got downloaded, you should see the same list that I have here. Now we're going to use RAM83. That stands for Rectangle Approximation Method for the TI-83. That's at least how it was originally written. But before we actually run the program, before we actually hit enter, this particular program requires you to pre-type the function into the y equals screen. The y equals screen is actually a storage spot for equations that programmers like to use. So we're not going to graph the parabola. Of course, if we did, I think we know what it's going to look like. But we're just using the y equals screen to store the equation because the program is going to look there in a minute. So hit enter so you can kind of like select that program command. You got to hit enter again to actually run the program. Pretty basic program. It's asking you for the left-hand point. Keep in mind that we're still doing the same problem that we did yesterday. It's from 0 to 6. And then the number of subintervals. Why don't we use the last sort of version that we did? We had 6 subintervals. That way we can kind of see the hopefully the same answer. Now I'm going to hit enter here. It does a little bit of calculating. And bam, you get your 3 areas. They are approximated areas, but notice that we got the left-hand area to be the same that we got before. That's 55. And now we have the other 2 areas to compare. And I would think that a nice thing to do with these areas would be to write them down. And of course, we're really writing them down so that we can use them to maybe even come up with a better answer. What would that better answer be? That's right, it's the average. Yeah, I can find the average of these 3 areas. Simply adding them together and dividing by 3. And we end up with 72.5. Now, remember what the average was the last time we did this with 3 subintervals? It was 74. So now it's dropping down a little bit to 72. One would have to argue that this answer is probably even better because it was calculated with more subintervals. Of course, more precision. So that's the RAM83 program. There's another program on here. It's called Viz Area or Visual Area. Why don't we try to use that program to find the area of this little parabola, x squared minus 7x plus 15 from 2 to 10. Now this particular program, I actually forget if you have to type the equation in ahead of time, just being honest. But the reason I am going to type it in is because in the end, the calculator is going to actually give us a visual answer. It's actually kind of cool. It's going to graph the problem. And if we'd like this to look nice, then we actually need to get the window a little bit more matching with the types of numbers that are in this problem. Now, what am I doing here? Well, simply I am extending my x-axis, or you might say I'm only using my x-axis to be closer to the interval 2 to 10. I'm not using exactly 2 to 10 because I'd like to go a little bit beyond. The other thing I'm going to do is I'm going to make my y-axis also sort of match a little bit better, particularly the y maximum. You see, if you plug the number 10 into this equation, you're going to have a y value up near 15. And so basically, I need more than what I normally get for a window. Now listen, some of this is some fluff and stuff, a little bit of making things look nice, but that's what the visual area program does. And if I want to see a nice graph, then I need to make my window I need to set up my window ahead of time. So we're going to run the Viz area program. This one has a little bit of a welcome screen. Just a comment, in the upper right corner, you should see dancing ants. That's at least what I call them, dancing ants. That means your calculator is paused. Maybe you've seen this before if you started pushing a bunch of buttons. But basically, if the calculator is paused, the way that you unpause it, the way that you advance to the next screen is by hitting enter. Now, when I hit enter, the program requires me to type in the equation. Just a little side note, all this is really going to do is just paste the equation into the y equals screen. I know I already typed it there, but I still need to paste it in. I need to type it into the program so that it doesn't paste in a blank. A is referring to my limit, my boundary. B is, of course, the rest of that boundary. So we're going to go 2 to 10. And did you notice that I said, let's do 20 subintervals? It's going to be quite a few rectangles, but hey, the calculator is going to do it for us. Now, when I hit enter, I get to another menu, another screen. Notice that it's paused because the dancing ants in the upper right corner. But let's do, what do you want to do? Let's do the LRAM. So my parabola gets drawn, my rectangles from 0 to 10, and it looks like the window I chose still wasn't really the perfect window, but hey, I can still see most of the graph, most of the rectangles underneath here, so that's good. That's the LRAM. It actually gives the value of it. Go back to the menu if I want to see what happens to the right. It still kind of looks the same, but if you're looking more carefully, you'll notice that those rectangles are actually a little different. They're actually sticking out of the parabola. It's going to give me the answer for this. And then I can also, if I'd like, I can get the MRAM, the middle. So Viz area, it's really just kind of cute. It shows you the answers. Although some of you, if the other program didn't work so well, like it kind of like skipped a screen. I know sometimes people tell me that different model calculators, you kind of like lose one of your answers. Maybe you just want to use Viz area because look, you can see all the answers. Now, how do I get out of this program? Because right now, it looks like I'm on the home screen, but I'm not. I'm in a program and it's paused. So the writer of this program gave us a way to get out. You hit the stop button. Now, it says done, so I'm kind of back to the home screen. I always encourage kids just to do some simple calculation to make sure that you're completely away from the program, because if you accidentally hit enter, the program will actually run again. But now if I hit enter, it's just going to do the last little command. So anyway, I don't want to accidentally get back into the program. How about this problem? Can we estimate the area under the cosine graph? Now, there's two things going on here. First of all, I want you to realize that I'm going to ask you to estimate area. This isn't just kind of like for fun because we're using the calculator. The second thing is, let's use the calculator, okay? If I ask you to estimate the area, you can use the calculator to do it unless you're told you have to draw it. But what you want to know how to use your tool. And one of those tools is to realize that if I had a lot of subintervals, like maybe 10 or 100 or 1,000, well, I should get a more precise answer. So I'm going to use the basic RAM83 program. I'm going to anticipate that I have to type the equation into the y equals screen. Of course, calculus is always done in radians. I don't really need to graph this or fool with the window. I just need to know how to run the RAM83 program. Now, 0 to pi over 2 using 10 subintervals. 0 to pi over 2 using 10 subintervals is going to produce these numbers. They might be numbers you want to write down. They might just be numbers you want to sort of tuck in your head. But if we're going to give an answer, I'm talking about like an actual final answer. Do you feel like you're ready to do that just by looking at these numbers? Oh, maybe I should average them. Oh, okay, yeah, now you're thinking. So if you average these numbers, you might get a better answer. What if did you see how I just hit enter to run the program again? What if I use more subintervals? What if I use 100? Now, one thing it's going to do is it's going to take longer. The calculator actually is calculating something. So we're wasting battery, but the calculator is working, and okay, finally out pops these numbers. Now, if you have a good memory, you remember what the other numbers were, and maybe notice that these numbers seem to be getting closer to maybe more like a true answer. Perhaps I want to average these numbers. Here's what we're getting at. You want to be able to make a conjecture. A conjecture is simply when you take your answers, or in this case, maybe your average, and you eventually say that I think that the estimated area, well, for this problem, would be 1. To kind of emphasize it with some decimals, like literally the number 1. Now, were any of the answers in my calculator exactly equal to 1? No, none of them were exactly equal to 1, but I'm making a conjecture. I'm noticing that they're getting closer to 1. I'm not going to use 1,000 subintervals. That's going to waste a lot of time and battery. But I feel pretty good about the fact that the area of this cosine graph should be getting closer to 1. Now, in the next lesson, we're going to visually look at cosine and realize that you just found a special area, because pi over 2 is right here, 0 is right here. You just found this area, and again, it's kind of special. For one thing, it came out to be exactly 1, or at least we're conjecturing that it does. And so we'll be looking more at this space that we found. Will be very interesting. You're ready to go now. You're ready to use your calculator programs. You kind of want to fool around with them a little more. You notice there's some that I didn't use yet. We'll get to those. But yeah, you have free reign to use the calculator programs. Of course, unless you're directed to actually draw out the RAMs, which you will be. But there's nothing else that I share with you about those programs. I just want you to start to play with them. There is one more thing that I'm going to share with you. It's an application problem. We're going to look at number 11 on page 255. Now, this isn't going to help much if you don't actually open your book up to number 11. I'm actually going to open mine right now. So please push pause if you have to. Get a book out. Seriously, this is not going to help you too much if you're not able to look in your book. Now, when you do look in the book, you're going to see an application problem. It talks about a tidal river. Apparently, there's like a stream, and I guess the water is moving. Okay. If water is moving, it's a velocity. So we have velocities that are recorded every 5 minutes. And then we can see those results are in this table. Now, kids, what this problem is sort of leading itself to is honestly a velocity graph. Just like we started with the train problem, if we think about the area under a velocity graph, we're going to be able to get a distance, which is what we're trying to find in this problem. If you notice, it says let's figure out how far the bottle travels. So we need a velocity graph. Now, one thing that's true about this problem is that, yes, it's an application problem, but it's also a scatter plot. I am not going to scatter plot graph every one of these points. I am, however, going to help you guys see a little bit of a pattern by looking at a few of the points at the beginning and a few of the points at the end. And when this is all over, hopefully we'll be ready to understand a little bit more about this area. So I'm going to start graphing some points. Just grabbing them off of the chart. This one, I'm going to just label the velocity. It's 1. I guess it's actually 1 meter per second. The next one I'm going to graph is at 5 minutes. It's like 1.2. It's just kind of an estimation, of course. What's next? The one at 10 is at 1.7, so it's a little higher. I told you we're not going to graph all of these, but I am going to graph one more, kind of at the beginning here at 15. I get up to 2. I guess we'll make it 2.0 just to kind of match with 1 decimal place. Now, there's lots of other dots, that is, there's lots of other velocities between 15 and 45. Each one of those dots would still be part of this graph, but they may not need to be part of our little sketch if we are able to see a pattern. Okay, so what am I doing? I'm just kind of grabbing the last few velocities. At 45, it's 1.8. At 50, it's 1.5. At 55, it's 1.2. And at 60, it's 0. I know it doesn't seem too amazing right now, but the truth is there is a graph. There is a line. And if I kind of connect these points, I can start to see that graph, which is the velocity graph, which maybe more importantly starts to create an area. There's definitely an area that is contained in here. And please don't forget about the area that is in between. Sometimes kids incorrectly just kind of forget about the rest of those points. I'm just trying to save us a few minutes by not graphing every point. Okay, now I'm going to get rid of these blue lines because I want you to see that if we now start to think about the LRAM, we can actually do the same thing that we did back yesterday when we were drawing some of these graphs. We can go to the left side of the interval and we can see a rectangle. If I go to the left side of the next interval, each one of my rectangles, notice, is going up here and it's meeting with the velocity. If I go out here to the end, I can go to the left side. Okay, now my rectangle is kind of like outside of the space. If I go to the left, for each one of these remaining rectangles, if I go to the left and meet the graph, then I'll generate these rectangles. Now, the area Well, it's going to be, of course, the sum of each one of these regions. Let's forgive me here. Let's actually use the same organization technique that we did before. So region 1, that's this guy right here. It's, of course, a 1 by 5. Region 2, that's this guy here, is a 1.2 by 5. Region 3, okay, which is that one, 1.7 times 5. Now, there's all the other regions in between here. Region 4, all the way to, what's my third to last region? It should be region 9, right? Because now I have region 10. That's this guy right here. Region 10, region 11, and region 12. And those are also 5. That's supposed to be an R right there. Those are also 5 units long, but a 1 by 8, or excuse me, a 1.8, a 1.5, and a 1.2. Now, we're going to add all these up, okay? But do I really want to multiply by 5, by 5, by 5 each time? I don't. So what I'm going to see here is that ultimately this is going to be the sum of each of these velocities. But I want you to note the velocities are starting with the number 1, but ending with not the very last velocity of 0, but ending with 1.2, you might say the second to last velocity. Now, I know that's what my diagram shows up here, but again, I want you to see that I'm not actually using the last velocity of 0. Notice I'm using the second to last velocity of 1.2. And that is what happens when I do an LRAM. Again, I'm going to use, well, basically all the velocities except for the last one. Now, when you add all these up, you get 17.4. But don't forget, you have to multiply by 5. You have to multiply by 5 because that's the other dimension, right? That's the other dimension. That's the other dimension of each rectangle. So we take 17.4 times 5, and that gives you 87. Now, it would be nice if 87 was my final answer. It's not. And it's not because we have a little mismatch of labels. This is kind of a tricky part of this problem. Oh, wait a minute. You're wondering how I got 17.4? You're saying that that's not what you get when you add up these numbers? Right? You're right, kind of. That's because I have all these numbers in here to add up also. Remember, kids, you have to add up all the numbers in the diagram, or I should say in the chart, even though I've only diagrammed the first 3 and the last 3. So please make sure when you add up all the numbers, you get 17.4. Of course, you don't use the last number. We didn't use 0. And I had to multiply by 5. Now, where were we? I was saying that it'd be nice if 87 was the correct answer. The reason it's not the correct answer is because we have a mismatch of time. You see, the table is in minutes. 5 minutes, 10 minutes, 15 minutes. That means the dimension was in minutes. But the velocities are measured in seconds. Oh, the velocities are measured in seconds. So what we have to do is we have to basically convert this. We have to convert this into so that they match. And we just need to know how many seconds are in a minute. If we multiply by how many seconds are in a minute, then we will make our units match. and we will come up with the true distance that this thing traveled over 60 minutes. 5,220 meters. Again, I had to multiply by 60 so that my units converted essentially into seconds. That's what I'm looking for. We have to convert this into seconds. Now, the answer is not meters per second. It's not a rate. It's just a distance. So I traveled 5,000 meters. That's a long time, or that's a long distance. I guess the stream is moving pretty fast. Now, we found the LRAM to be 5,220, but don't we usually at least have a couple different RAMs to sort of average? Yes. That means that we're going to do this problem again, but we're going to do it with the right RAM. Now, I'm going to go a little bit faster this time, but the truth is I still need a sketch. Honestly, I'm only going to sketch the first few, and just like before, the last few sort of data points, hoping that you can see sort of a pattern here. Don't forget about the points that I'm not sketching. They also become part of the final calculation. Now, some of you would at this point may say, could I just do this on my other graph? You can. I'm not going to do that because that will definitely confuse people. There's going to be too many numbers and lines. I'm going to recommend that you do this on a new graph. But if right now you're graphing these, again, kind of over top of your other graph, that's your call. Now, each of these first few and last few data points generate what appears to be the same scatter plot. If I even think about connecting a line, I still see that there's a space under here. That's until I actually go to the right of each of these intervals. See, if I go to the right of each of these intervals and go up and meet the graph, I actually have a different rectangle already. The truth is, each one of these rectangles is different. I'm referring to the y values that we're actually going to be using when we get ready to do some calculation. Yes, you're right. You can see that the first y value is not being used. Okay, the first y value is not being used. Let's see what happens over here. If I go and make my last few regions to the right, okay, when I go to the right, I don't really get a rectangle, but look what y values are being used here. The truth is I'm going to finish with all of them. You see, when you use the right RAM and think about each of these regions, you're going to, this is supposed to be region 10, this is region 11, region 12, it's 0, but we'll still put that down. But to say it again, when I do the right RAM, I'm actually going to skip the first y value. If you kind of organize it, maybe this is a little overkill at this point, but if I organize it, I can see the first number I'm using is 1.2. Of course, you have to multiply each one of these by 5. That's the width of your interval. I'm going to have all the ones in between here, but ending with 10, 11, 12 is going to be 1.8. That is not correct. Sorry, I should have looked back up at the screen. It's 1.5, and then 1.2, and then 0. Listen, the whole point here is that you're going to add all of these numbers together. But I'm not using the first number. Again, I'm not using the number 1. But I really am going to add all the other numbers in my table. And when you add all those numbers in the table, you get 16. Now, notice I didn't multiply every one of them by 5. I might as well just multiply by 5 at the end. So where did I get 16? I added these y values. Of course, I added all the y values. That means the ones that are in between. But I did not use the first one, which, one more time, the first one was 1.0. And so I end up with a different answer. I end up with 82. Except 82 is not really the right answer because you have to multiply it by 60 to make the times match. I really end up with 4,920 meters, which if you have a good memory, you realize that's a little bit less than my other answer, but that's okay. I'm going to use both answers. We're going to find the average. It's kind of the best we can do. And at that point, I end up with what I'm going to argue is the distance that that bottle traveled. It's at least the best answer that I can find. Now, so a little bit, there's a lot to this problem, but in the end, it's really just adding up the y values, making sure that you're using the correct ones, and if you use the right RAM, you leave out the first y value, but if you use the LRAM, you leave out the last y value. Essentially, that's what's happening here, okay, because each one of those y values is a dimension of a rectangle. Now I'd like you to do a little problem. I want you to draw a sketch. I want you to draw some rectangles. Notice I'm going to ask you to do the LRAM by hand, by a drawing. You can use the calculator programs to continue finding your RAMs, basically the remaining RAMs. And then I want you to make a conjecture. The conjecture means that you're going to look at your answers and kind of come up with what you think is really the right answer. That is the most right answer that we can argue for an estimation. An estimation of the square root of x plus 4. Okay, so you're going to use 4 subintervals. I'm just kind of making that decision, use 4 subintervals. And this is something that you can do on a little half sheet of paper. For some of you, it's something that you have to do kind of as a little homework, a little bit take it home, that's fine. But please make this the final part of today's lesson.